So once again, we've got this wheel with all the mass concentrated at the rim. It's a hoop, and 1,000 Newton mass, 1,000 Newton force acting always tangent to the circle. Circle has radius r. We want to know what the angular acceleration is, the angular velocity, and the change in angular position up to time t if this thing starts from rest. So, first of all, we've calculated, well, we've got the expression for delta S. Okay, whatever t is, it'd be 1/6 meter per second squared times t squared. And delta S is just r delta theta. That's the definition of a radian. Okay, and we actually mentioned this just briefly right here. Our definition of the radian is we've got a circle of radius, whatever, and we've got angular displacement here, that the angle is 1 radian if delta S is the same as the radius. Okay? In other words, a radian is the angle where your arc distance is equal to the radius of the circle. It follows that the displacement is radius times delta theta, and this is something we've established a long time ago. If your delta S is 1/6 meter per second squared times t squared, what's your delta theta? Well, you simply divide that, well, you divide your delta S by your radius. Now, one condition that we have is now that r is 4 meters, circle of radius 4 meters. So we divide the quantity for our distance along the arc by the radius of the circle, and we get the result. The delta theta is 1/24 radian per second squared times t squared. Follows immediately. And from this, it follows that omega, being the derivative of theta with respect to t, is 1/12 radian per second squared times t, and then that the angular acceleration, being the derivative of the angular velocity, should be 1/12 radian per second squared. Now, of course, we calculated the speed, the 1/3 meter per second squared times t, and we could also calculate omega by simply dividing the result that we already got by the 4 meters to get this. So this is both what we get when we divide the speed around the arc by the radius, and what we get when we take the derivative of our theta function. Similarly, we worked out immediately that our acceleration was 1/3 meter per second squared. We get our angular acceleration by dividing that by the 4 meter radius, and that agrees with what we get if we take the derivative of this expression.